My name is Sarah, and I'm the head of youth services here at the library. It is my pleasure to introduce Christopher Skinner, who joins us from UMass-Lowell tonight to talk about extreme weather, hurricanes, and climate change. And as always, thank you so much to the REACT grant from IMLS for sponsoring this program. Enjoy.
Great. Well, thank you very much for the invitation to come speak today. I'm going to talk very broadly about climate change, and I'm going to talk about hurricanes, and then I'm going to talk about the question that I get asked pretty much every week, which is, does climate change cause hurricanes, or does it cause, insert here, extreme event that just happened in the previous week. So the first time that I was asked to talk about this question, this connection between climate change and hurricanes, was in November of 2017. And they actually gave me a title to my talk. They said, I want you to give a talk, and the title needs to be, does climate change cause hurricanes? And I thought that was, or does global warming cause hurricanes? And I thought that was kind of an interesting title. But I typed in, does global warming, into Google at the time, and sure enough, the second suggested completion to that statement was, does global warming cause hurricanes? And so it was a very popular thing to search in 2017 during the fall, and I'll describe why that's the case in a minute. Right before I came here, I typed it into Google 2 years later, or almost 2 years later, and it doesn't even come up on the list. So you can interpret that in two ways. There's a positive way to interpret that, and that is, if you look at these lists, they're pretty much entirely different, with the exception of, does global warming exist, which seems to always be around. What this does mean is that people are recognizing that climate change is impacting us in a lot of different ways. And so it's really permeating pretty much all aspects of our lives, and so people are asking different questions about it. It also highlights, in a slightly more negative viewpoint, it highlights the fact that we have recency bias. And if hurricanes aren't constantly hitting the United States, people tend to forget about this connection between the two. So why was this such a popular topic in 2017? Well, this is a satellite image, a real satellite image from September 6th. And there are 3 hurricanes in the Atlantic Basin at the exact same time. And they're not just in the Atlantic Basin, they are clustered together in the Western Atlantic Basin. This is pretty rare. It is not unheard of to have 3 hurricanes in the same basin. That happened in 2010 as well. But they've never all been in striking distance of land before. So this is the first time that happened. So people were very curious about this connection. To give you a little bit more context, in 2017, what I'm showing here is a map of the different trajectories that all of the tropical cyclones took in the Atlantic. So a tropical cyclone is an umbrella term for tropical depressions, which are the weakest of the tropical cyclones. So when you have winds that are less than 39 miles per hour, that's a tropical depression. If that tropical depression intensifies, it becomes a tropical storm, and that's up to about 74 miles per hour, sustained winds, and then you reach hurricane status after that. So there was 18 tropical depressions, and 17 of them made that jump in intensity to tropical storm level. And of those 17, 10 of them became hurricanes, which was quite active. Of those 10, 6 became major hurricanes. So a major hurricane is anything that's a Category 4 or a Category 5. So winds above 130 miles per hour. So that's a sustained wind measurement, not a gust. So gusts can exceed these values, but at least 1 minute of winds above 130 miles per hour. So this was, again, not the first time that you had 2 Category 5 storms, but it was only the second time that you had 2 Category 5 storms hit land. So quite anomalous in that sense. And there's some other anomalous things that happened that I'll get into. But it also was the season in which we had Hurricane Irma, which is the strongest hurricane ever recorded in the Atlantic. So winds with Irma were 180 miles per hour. And if you're curious, that's not the strongest hurricane ever. There was Hurricane Patricia in the Pacific Ocean, which I believe exceeded 210 miles per hour. But that was also a recent phenomenon. So in total, just these tropical cyclones in the Atlantic resulted in at least 464 fatalities. This number is surely higher. This is very conservative. And $320 billion in estimated losses. So some of the systems that you might remember from 2017, Hurricane Harvey is one that really stands out. This is the one that hit Texas and stalled over Houston for 3 days. And in Nederland, Texas, which is just outside Houston, I think, received 60 inches of rain. That's on average, that would be an entire year's worth of rain for that town. So it's just amazing. In total, if you sum up all of the water that fell on the Gulf states, so not over ocean but over land, that equates to 33 trillion gallons of water. So if the Washington Post actually made a graphic of this, what 33 trillion gallons of water looks like next to the city of Houston. So it would be a box or a cube 3.1 miles on each side. So it's just a tremendous amount of water. And that flooding was made worse not only because the system stalled and dropped so much, but because of urban sprawl. You have impermeable concrete surfaces. These roads were actually designed to act as flood channels. They did work in that sense, but that was part of the reason why there was so much flooding. Hurricane Irma. This is a satellite image of the island of Barbuda before and after Irma hit. So this is August 27th of 2017, and this is September 12th of 2017. And this is the storm that was the strongest hurricane ever in the Atlantic Basin. Like I said, 180 mile-an-hour winds, and you can see that the vegetation is completely gone on the entire island after Irma hit. That's a combination of winds ripping the leaves right off the trees, but also during hurricanes, salt is kicked up off the ocean and deposited on top of the vegetation, and the salt desiccates the leaves, and so they die and they fall off. And then lastly, of the major ones that we remember was Hurricane Maria, which hit Puerto Rico, and this one was primarily remembered for the power outages across the island. It took nearly 7 months for power to return to Puerto Rico. So damaging winds, but also just a tremendous amount of rainfall. So most of the island saw anywhere from 18 to more than 2 feet of rainfall from this storm. And this one actually, I believe, was Category 4 when it hit, but it hit, I forget which island it hit, but it hit another island at Category 5 status. So it was very, very damaging. The last one I want to bring up, which is less severe, but unique in its own right, was Hurricane Ophelia, which is the easternmost Atlantic hurricane ever recorded. And so this is it here, and I'll let this loop through again, but the interesting thing about this one is it took such a bizarre track to the east that it actually started to interact with a wildfire that was going on in Portugal at the time. And so this is Saharan dust, and as it hit there, it actually fanned the wildfire in Portugal, made it worse, and brought smoke all the way up into northern Europe. So sort of two extremes here. Wildfire certainly is something that we've now recognized as increasing because of climate change, because of drier conditions, and then potentially changes in the hurricane tracks from climate change as well. So sort of a collision of two worlds there. So it was a pretty devastating year. And this talk is not uplifting, I should say that now. But I'm going to give you a status of climate change in 2019, because we can't really talk about the connection between climate change and hurricanes if we're not versed in what's going on. And then we'll talk about detecting human fingerprints on hurricanes, which is sort of drawing the connection between the two. Is climate change from humans influencing hurricanes? And then I'll talk about some projections of the future. And I'll also, throughout this, interject some local climate data as well, because I'm sure you're interested in that. And stop me at any time if you have a question. I'll do my best to answer it. So the status of climate change in 2019. So this is a map of temperature for the year of 2018, which turned out to be the 4th warmest year on record, trailing 2015, 2016, and 2017. So the 4 warmest years have occurred in the past 4 years. It was 1.42 degrees Fahrenheit above average. What this map shows is for each block, it's just matched the colors. So pink is warmer than average, blue is cooler than average, And wherever you have really dark red, you've actually exceeded your records. It's the record warmth. So a very warm year. Not the.
I don't want to get too deep into this, but how did they come up with that figure? Is it just an average for the day and then you divide it by 365, or?
So I'm not sure which it's a good question. I'm not sure which data set they're using. But I'm assuming it's a daily. You take a daily average temperature, and then you have the average for the entire year, average across the days. You could do that with hourly temperatures, but
Where is that measured?
these are measured. This is a combination. So there's over land there are a lot of different land-based stations where you're just taking like a thermometer measurement. In the ocean, you have a combination of buoys and ships taking measurements. And these also include satellite data. So you can put satellites into space and get a temperature reading as well. Where you see these grays, and to this point here, where you see these grays, that's where we don't have a very long, robust record of temperatures because we haven't been measuring them there for a long time. We have them now, but to make this type of plot, to put this into context with the 100 years before it, we can't really do that in these regions because we don't have good records there.
Going back in time, is there enough corresponding data from years ago to make this a valid?
Yes.
trend?
Yes, not in the regions that are gray, but everywhere else, yes. And there's other ways to get these measurements through paleoclimate proxy records as well. But this is entirely observation-based, so direct observations. And this is just one output. This is just from NOAA, the NOAA National Ocean and Atmospheric Administration. This is just one of 3 or 4 data sets out there that all confirm what each other is saying. And so just more recently, what was going on in the most recent month that we had, that was March. It was the second warmest March on record. And if you look at Alaska, averaged across the state of Alaska, it was 16 Fahrenheit above normal, which is outrageous. It was the warmest March on record by a lot. And we'll talk a little bit why that is, but it has to do in part with sea ice melt just north of Alaska, which is at a record low right now. So put this into context, sort of in a bar plot here, going back to the late 1800s where we have pretty good records starting. This is the anomaly, so the difference between the temperature in that specific year and the average over the 20th century, so 1900 to 2000. You can see this very clear upward trend here. 2016 was the warmest year on record. That was an El Nino year. El Nino years, that's when you have natural variability on top of this warming trend, and those are generally warmer than usual. So those two things combine to make 2016 very warm. This is 2018 here, but now even years where we're not in an El Nino, like this year and last year we were not in an El Nino, those years are now warmer than all the previous El Nino years, which is just an indication of how much the mean global temperature has been increasing. So just to really hammer home that point, 18 years after 2000 rank among the 19th warmest years. So the only year that's not from the past, or since the year 2000, is 1998, which was a very strong El Nino year. So like I said, they're all exceeding the El Ninos of the past. So what about Massachusetts? Well, this is the plot, same plot, but just in line format, going back again to about 1900 here. And the blue line is the linear trend. So this is your average temperature. Yes, average is this gray line here. So average temperature over this time period was about 47. So back in the early 1900s, your average temperature in Massachusetts, the average annual temperature, so that's the whole day's worth of average, was about 46 degrees Fahrenheit. And now it fluctuates certainly every year, but we're looking at something more like 48 and a half, closer to 49. So temperatures are warming roughly 0.2 degrees Fahrenheit each decade. And if we want to look at that in sort of seasonal format here, so each month is on the x-axis and your average temperature on the y-axis. The blue colors here are the 5 coldest years since about 1900, and the warmer colors are the 5 warmest years, and this green one here is 2019. So right now we're sort of right in the middle. Black is your median, or your average actually. So yeah, it's kind of hard to say what's going to happen over the next few months, but it doesn't look like we'll be on track to be one of the warmest years because it's going to be a pretty weak El Nino year. But Certainly above normal again. So what does that mean? So warmer temperatures obviously have impacts associated with them themselves, but they also do things like increase the moisture in the atmosphere. So this is a plot of temperature on the x-axis and what's called saturation vapor pressure. So essentially just the point where air becomes saturated with water. And so as you increase the temperature, you are able to hold more water in the atmosphere is effectively what that means. This is known as the Clausius-Clapeyron relationship. It's been known for a very long time. So with each 1 degree Celsius that you warm, the air can then hold 7% more water. So we can actually track that. So since the 1970s, late 1970s, we've been tracking how much moisture is in the atmosphere. Again, this is from satellites primarily. And this is land and ocean, and we see an upward trend in the amount of water vapor in the atmosphere over that time, which is directly following this relationship here. So what does that mean? Well, more water in the atmosphere means that you have the potential for stronger rainfall events. So this is a map it's put out by Climate Central, who makes a lot of really nice graphics. They're just using, again, publicly available climate data that we can all download, and just showing how what they're defining as a downpour. This is sort of a subjective measurement here, but it's 1 inch or more rain in a day, and sort of how that's changing over time in the United States. So this directly follows that relationship where if you have more moisture in the air, when it does rain, you have more moisture that can possibly fall out of the air. So that's a pretty straightforward measurement. It doesn't require any models or anything like that. And what does that look like in Massachusetts? Well, that's on the right here. And it's going back to 1950 and going through to the present, or just short of the present day. And it's the number of heavy downpours, again, defined by 1 inch of rain per year. So in the 1960s, 1970s, and I should say this plot here comes from the airports in Massachusetts. So there's not that many. But on average, you were receiving about 8 per year, and now we're looking at something like 14 to 15 per year. So a pretty dramatic increase. And it's happening everywhere, not just Massachusetts, with the exception of the Southwest, which if there isn't moisture to evaporate and put into the air, you generally don't see that increase in downpours. And so it's a very dry area, so that follows. So sea ice. So this is sort of what's in part driving that Alaska 16 degrees Fahrenheit anomaly. On the right, which you're probably drawn to, this animation, this is the sea ice extent for every September. So September is when sea ice is at its minimum each year, and this is how that's changing since the late 1970s, or 1981 maybe, or 79, and going up to 2017. And it fluctuates every year, and that's largely driven by weather, but it is certainly decreasing, and you can see that in this animation. That's just plotted here as well, so averaging across the whole Arctic, giving you an extent for each month, so starting in January and going into December, and there's that September minimum. And so these are the most recent 10 years, and they're all the ones that I've highlighted here. And this gray range, so this gray is your median, and this is your 10th and 90th percentile, so basically establishing a range of all the previous years, and all these years have now fallen below those. So sea ice is certainly hitting new records. The lowest was in 2012. Here's this little orange line here I tried to highlight is 2019. We are currently in a record low. Whether this is going to continue, who knows? But generally, if you're in a record low here, it's easier to hit a record low here. So we'll see. But certainly right now, there's a record low in Alaska, which is contributing to those warmer temperatures. So it's not just sea ice, it's also land ice that's melting. And this is an image. I'll get to this in 1 second. This is the reflectivity, again measured from space, of Greenland's ice sheet. And so if it's a reflectivity anomaly, so it's relative to some baseline period, probably the end of the 20th century, I kind of forget. But what you see is where there's blue means that it's less reflective. And the reason for that is that there's usually a lot of snow on top of the ice sheet, which makes it very reflective, a very high albedo surface. As that snow is becoming less common and melting, you're revealing stuff like this here, which is dirty old snow. And when the sun is beating down on that, it actually absorbs the sun's energy rather than reflect it to space, and that causes more melting. So Greenland is melting at a fairly fast rate as well, just like the sea ice. There was actually in 2017, and I think it was down here, I forget exactly, but ice has been retreating a little bit, and there was actually a wildfire in Greenland, and that wildfire then emitted a bunch of soot and black carbon particles on top of the snow here, which then accelerated melting even further. So sea ice, land ice, all melting, and that's contributing to sea level rise. And this is a major concern to Massachusetts in particular, at least for the coastal communities like Boston. And so this is a measurement since the early 1990s. We have fairly accurate measurements of how sea level is changing, again from satellites. And right now we're averaging about 3.4 millimeters per year of rise globally. And so if you were to project out for the 21st century, by the end of this century, fairly conservative projections are that we will see about 1.5 to 3.5 feet of sea level rise. And those projections come from climate models, which I'll talk about. Those do not include sort of catastrophic melt from Antarctica, so it could be a lot higher if that was the case. So getting to this connection between climate change and extremes, well, we really care about these extremes primarily because they're very dangerous. They cause a lot of human loss, ecosystem loss, and they're very expensive. So this is just a map of 2018 billion-dollar weather and climate disasters. So just the ones that cost at least $1 billion in damage. So collectively there were 14, and they caused 250 deaths and $91 billion in losses in the United States alone. So hurricanes are on there, the fires in California, the Camp Fire, even winter storms, hail, tornadoes. Basically everywhere in the United States gets hit. It's the U.S. is unique. It gets wildfires, it gets hurricanes, it gets tornadoes, it gets blizzards. There aren't that many other places in the world that experience weather like this. And this is happening regardless of climate change. But certainly if we look across time, the number of these events is increasing. So this is a plot going back to 1980 to the present day, broken down by each type of event. So how many of these billion-dollar events of each type? And certainly there's an increase here. And this is, of course, in part driven because we're exposing more assets. We have more property in harm's way. So that's absolutely a reason why this is going up. But at the same time, we are adding energy to the climate system by trapping in heat, and that contributes to this upward trend as well. So what is causing that? Well, it's CO2. It's not a question. CO2 is increasing. So this is a measurement of CO2 concentration in the atmosphere beginning in 1960. This comes from Hawaii, which is a very pristine area to measure something like CO2. And you can see this has been increasing from about 315 or so up to, we're currently at about, well, right now we're at 413 ppm, last time I checked, so April 16th. If you look at this and you're wondering why is there this squiggly nature to it, I sort of blew it up here from July to January. That squiggly nature of CO2 concentration is related to vegetation. So we actually peak in the late spring, and then as vegetation blooms, the vegetation takes in CO2 for photosynthesis, and our CO2 concentrations actually drop throughout the summer and into the fall, and then they begin to build again because there's no vegetation. So that's what's explaining that exact pattern there. So CO2 is rising. In 2018, it rose by 2.2 parts per million. That's how we measure this. So it's how many parts of CO2 in the atmosphere for a million parts of air, essentially, how many molecules. And we know this is from humans. It's very straightforward. We're burning combusting fossil fuels. But if you go back looking at ice core records that go back 800,000 years, you can get measurements of what the CO2 concentration was. It's trapped in the ice bubbles, and we have not reached a level as high as we are right now during that entire span. There are some estimates that say we haven't reached this level in 10 million years. That's not my area of expertise. I'm not quite sure where they get those numbers from, but they're from other proxies. But this one is very clear. We have not exceeded it in 800,000 years, and it's going very fast. and this is humans. So who is responsible out of the humans? Primarily us for a while, and then China and India have been contributing as well. So this goes back to 1960. This is CO2 emissions. So I believe this is from all types of different processes, so cars, heating, electricity, everything. Yeah, and 2018 is projected on there. So these are actual measurements, and then this little dot here for each one is what was projected for 2018, because this plot was made at the end of 2017. So for 2018, emissions rose by about 2.7%. So we're supposed to be slashing emissions right now if we want to meet things like the Paris Agreement. So we're not doing that. We had stalled for a few years. For 3 years, we actually hadn't seen any growth in CO2 emissions, but China has, in particular, China has increased their emissions through some stimulus that their economy's down, so they injected a bunch of money into construction, and so that's actually driven emissions back up. So the US has actually increased as well over 2018. That's largely driven by the fact that last year had a very cold winter and a very hot summer, so we use more energy. On a per person basis, it's not even close. The US is burning the most fossil fuels and emitting the most CO2 into the atmosphere. So this is sort of a per capita plot here, the US, and then China is increasing, but so China, the EU, the rest of the world, India are considerably lower than the United States. Yeah?
What's accounting for the European Union decline?
Largely, so the US is doing pretty good in that regard too, with the exception of this year. Largely a transition towards natural gas. That's a big contributor to that. So we're switching from coal to natural gas. We should be switching to renewables, not natural gas, but that is an intermediate step that has contributed to that. So before I get into the connection between hurricanes and extremes and climate change, this image is one that I always think about. They've become so common, extreme events have become so common that we play golf through them. So this is from Oregon, this is 2017, I believe. And these guys decided that this was not alarming enough to them that they could finish their round of golf. So I've been assured that there is a river right here that we can't see, that they felt safe, but as we know, wind can blow across the river and cause a fire on the other side. So, okay, so that was the overview of what's going on. And so what about detecting human fingerprints on hurricanes? So can we attribute specific events, specific extreme events to human activities? So there's two ways to do that. And these are very active areas of research in climate science. And this, I should say, this is a pretty new field. It really wasn't around 20 years ago, but advancements in computer modeling in particular have made this a much more active area. So I'm going to briefly talk about the two different approaches in a very scaled back, simple way. So one is called the ingredients-based approach, and the other one is a probabilistic extreme event attribution approach. So I'm going to start with the ingredients-based. So in this case, we don't try to say something about the specific event. We try to say something about the ingredients that contributed to that event. And that'll become more clear when I go through an example with hurricanes. So rather than say, yes, hurricanes have become more common because they are particularly hard to simulate in a computer model, what we can do is say, okay, the ingredients that contribute to hurricanes are either becoming more or less common because of human activities. And so to answer that question, you have to know what causes a hurricane in the first place, and there's four main ingredients. The first one is an initial cluster of thunderstorms. Warm water is another one, moist air, and light winds, or low wind shear in the atmosphere. So is global warming influencing these ingredients? I'm just going to very quickly go through. So the first one is an initial cluster of thunderstorms. This is what I've spent a lot of my PhD studying. And I'm not sure everyone knows this, but 70% of tropical cyclones actually originate as storms over the Sahel. So the Sahel is this region right between the Congo and the Sahara. It's this sort of strip here. And so a thunderstorm forms here, and it develops, moves off coast, and can turn into a tropical cyclone. So about 1 in 7 of those becomes a tropical cyclone, and they account for 70% of all of them. So the question is, are these systems becoming more common, or are because of human activities? The simple answer is it's unclear. We don't know. These are not well studied. They're very difficult to simulate in a model, so it's hard to isolate what's going on there. So the answer to that is unclear, so we can't necessarily attribute that particular ingredient. But what can we say about the other ones? Well, warm water, perhaps not that surprising. We absolutely can say that the water is getting warmer. So this is a plot of not air temperature, but water temperature. Again, where it's white, we don't have enough data, but where it's red, we do. And this is the change in sea surface temperature from the early 1900s to 2015. And sea surface temperatures are increasing essentially everywhere with the exception of just to the right of Greenland, which is largely because water is melting off of Greenland and disrupting sort of it's called the conveyor belt, but there's usually a lot of mixing here and it's being disrupted. So cold water's not sinking there as it should be. And so if we're thinking about Hurricane Harvey in particular, this is a map of what the sea surface temperatures look like in August, and then you see a blue blob. This is where Harvey hit, and then it turns back to yellow. So temperatures were about 1 to 1.5 degrees warmer on average when Harvey hit. And this blue that you see here is actually right after Harvey hit. It churned up so much water from below that it cooled down the temperatures, so we actually picked that up. But so absolutely, temperatures were a lot warmer during August and September, and that's what helped fuel all of those tropical cyclones that we saw in that first plot. So yes, absolutely, human fingerprint on warming sea surface temperatures, which we know contributes to hurricanes. So moist air is another one that we know, right? We just talked about this one. Moisture in the air is increasing because we're increasing the temperature. It's this very simple relationship here. So that's a definite yes. And the last one is light winds or low shear. And this one is, again, a bit more unclear. So if you want to have an active hurricane season, you have to have low shear. So that means that winds near the surface of the Earth going in this direction, for example, and winds higher up in the atmosphere, they need to be going roughly at the same direction and sort of at the same speed. If they're going in opposite directions, or if the winds on the surface are going pretty slowly and the winds up top are going really fast in the same direction, effectively what that does is rip apart a hurricane, which is sort of like a heat engine. It needs to be aligned vertically. And so if it gets tilted like this, it can kind of shut itself down. And so what happened in 2017 in particular was it was a La Nina year. So it's the opposite of El Nino. That means we had very low shear, and that contributed to an environment where a lot of hurricanes formed in the Atlantic. So that was driven by natural variability, not necessarily anything that was human caused. So this is, again, unclear. We don't quite know how shear is changing as a result of human activities. So summing that all up, putting it together, two ingredients absolutely have increased because of human activities. That's the warmer temperatures and moisture. But in 2017, it was so active because it was let's see, El Nino reduced wind shear. La Nina reduced wind shear, allowing storms to persist. And impacts, of course, were made worse from sea level rise, which certainly is human caused as well, and human infrastructure. So there's other ways in which the humans are sort of making these storms more high impact that are not related necessarily to climate change. So that's the ingredients-based approach. That's how we sort of approach these topics. So if someone asked me, do hurricanes increase because of human activities? The number, no, but the intensity of the hurricanes, yes, is the answer to that. The other way to do this is a probabilistic extreme event attribution approach, which is a little bit complicated, but I want to quickly go through it. So in this case, we're not looking at the ingredients. We're actually simulating a specific event, and we do it in two simulations, one that has human emissions of CO2 and one that doesn't, and then we compare the probability of those events happening in the two simulations. And so I'll go through that here. So to do that, we have to use climate models. So this is what I do in my research, is run climate models, which are very similar to weather models that make the forecasts over the next few days. They're different in a few key ways. One is that they're run at a much coarser resolution. So a weather model might be run at like a 12 kilometer or 4 kilometer resolution. These are run at about 100 kilometers, so much bigger scales. And they're run for very long time periods, so we can run these for hundreds of years to thousands of years to do really robust statistics. And so this is an example. So this is what a satellite of the Earth looks like, is animated here. So this is actual satellite measurement, and this is a climate model. They're running at different speeds here, but the point that I'm trying to make is that these climate models, these are not like just statistical models. They are very dynamic, very, very impressive pieces of computer code that can, certainly they have biases, but they do a very, very good job of simulating these processes that we know impact people, like big tropical storms, for example. So they're very, very impressive. So to do this type of work, like I said, you run two different types of simulations. You run one where you include greenhouse gases over the past 100 years, how they've changed, and then you run the same exact model, but you don't include the increase in greenhouse gases. It's as simple as that. And you just plot the two up. So this is an example for temperature. So black is what's actually happened. This is our observed temperature anomaly over time, which we've already looked at. And then if you didn't include greenhouse gases over that time period, you'd get this green line here. And when you do include greenhouse gases, you get this blue line here, which matches the observation. So that's the sort of the simple analysis there. What you actually do is then not look at temperature, you look at hurricanes or heat waves or whatever it may be in the two simulations, and you test whether or not they're different from each other. So then we can say, yes, in the world where humans emitted greenhouse gases, X event was 20% more likely. So that's the way that works. And there are some caveats there. There are certain events that we can't say anything about because the models don't simulate them very well. So severe convective storms, that's one of them. So that's why I couldn't say anything specifically about how those storms over Africa are changing. As you grow in scale, and sort of very easy ones, like extreme heat, extreme cold, very easy to, we have a very good understanding of what forms those events, and we can simulate them very well. Droughts, extreme rainfall, those also are closer to this end here. Tropical cyclones sort of in a gray area there, so it's hard to do this approach with tropical cyclones, but that's why we do the ingredients approach. And so just as an example, what have we looked at in the past? Well, there is strong evidence for human influence on the European heat wave in 2003, which caused 30,000 deaths. The California drought, 2010 to 2015, fairly strong evidence that was increased in likelihood because of human emissions. 2016, there was flooding in Louisiana. But then there are other examples where there was flooding in 2013 in Colorado, and there was no evidence that human emissions actually increased the likelihood of that event. So it's a per event sort of thing. You have to do it for each one. But that's the other technique that we use. So with all that in mind, let's talk about the future a little bit. So we have some choices that we can actually make, which is the positive thing. So these are, on the top, different pathways that we could take. So the years on the x-axis and the carbon dioxide concentration on the y-axis. And so 2000's about here. We're now a little bit above 400. So if we take a sort of a business as usual, this is it's called a high emissions scenario, this red line here. So if we continue to burn fossil fuels and population increases, I think in this scenario, population increases to about 12 billion people globally by 2100. This is a fairly extreme scenario. Then our CO2 values will be about 900, 930 parts per million. And this is the temperature, the potential temperature change that we'll see over that time in degrees Fahrenheit here. And this range here is you run like 30 different models, and they all are slightly different, and so you get a range. But they're all certainly showing the same increase. And then you can take a less severe track here where we maybe incorporate some renewables. Population doesn't grow quite as much. That's one of these tracks here. And then we can do a very low emission scenario, which is 2.6, which already seems not possible. This would be like what does it say? Yeah, less than 2 degrees Fahrenheit warming, which is quite low. Right now we're shooting for 1.5 C or 2 degrees C, so that one is pretty much out of the question. But this 4.5 is certainly still in the cards. So looking at the United States and North America in general, if we do take this lower emission scenario, we're on the left here. If we take the high emissions scenario, we're on the right here. So emissions being primarily CO2. So this is by the middle of the century, this is by the late century. So in a middle of the road type of scenario, which we could do, our temperatures in the Northeast, for example, are anywhere from 4 to 6 degrees Fahrenheit warmer on average across the year by the end of the century. If we take the high emission scenario, we're looking at something closer to 8 to 10 degrees Fahrenheit warmer in New England, warmer towards the Arctic where you have Arctic amplification, which we're already seeing. So pretty different climates, and both totally within range. We could make either of these happen. Thinking more about extreme events, so days that the temperature exceeds 90 degrees Fahrenheit. This is, again, the middle of the century, so by about 2050, which is actually not that far off, 30 years from now. This is averaged across a bunch of different models, how many more days per year. And if you're looking at the Northeast, you're anywhere from 0 to mostly 10 to 20 more days per year. You can do this sort of, it's not smart to take a climate model and pick out a single point like Boston, but this is, I think, averaged over a region of Southeast Massachusetts, or Southeast New England, sorry. And so in 2000, we have about 5 of these events per year. 2030, we're looking at 8. And by 2050, we're looking at 16 days where they're called danger days. These are similar to these days, but they also include humidity, those days that it's really hard to sweat and very uncomfortable and very dangerous. Looking at 16 days per year, so double 2030, so quite high. It also means that we're going to have less freezing days, which some people think is good. So this is number of days below 32. So these are all negative values here. So anywhere from 10 to 30 less days below 32 Fahrenheit, which is not good for ski resorts. It's also not good for maple syrup, this was my first ever project as an undergrad. I worked on the connection between climate change and maple syrup. And I look back at that project now, and it is so simple and not that good. But when you do maple tapping, you tap the trees, you do it during the spring. You don't do it during the rest of the year. This is when the syrup tastes the best, and it's also when it's flowing. And so you actually, to get syrup to flow out of the taps, you actually need the nighttime temperature to drop below freezing. And then during the day, it needs to rise above roughly 36 degrees Fahrenheit. So you need that freeze-thaw cycle, and that's what causes the syrup to actually flow out of the tap. So this is a big business. Vermont is the leader for the United States. Canada is the leader worldwide. But in the U.S., maple syrup production was valued at close to $150 million in 2016. And this is where it's currently active. So what we showed was, well, there's this connection between temperature and maple syrup. So what does it look like if we increase temperatures? Essentially what we find is that the day in which you need to tap your trees moves much, much earlier in the year. So if you look at this is sort of like the high, the low for each day. It's temperature. Basically, you're just shifting it from what was in the late winter, early spring, much, much earlier into winter. Basically, you've raised the temperature upward, and so this whole thing has to shift down, this window. So what we found is that in northern New England, these locations here, you don't actually lose out on any maple syrup days. You just have to tap earlier, so there's some adaptation there. But places like down in here and even in parts of Massachusetts, you are losing out on days because you are, like we saw, losing out on the number of days that are below 32 Fahrenheit. So losing out on cold days is not all good. And then if we look at precipitation, the last thing I wanted to show, we know that temperatures are increasing. That increases the moisture in the atmosphere. Looking at across models, these are going out into the future. How many more days with at least one inch of rain per year? So this is a combination of low emission scenario, high emission scenario, throw it all into one plot. So these are the low emission scenarios, these blue ones, and these red ones are the high emission scenarios. So you're looking at, again, another increase averaged across all of Massachusetts of a few days per year of very, very heavy rain. So I wanted to highlight this website. If you're curious about what's happening in Massachusetts, this is the website that you should check out for climate data. It's called Resilient MA. I just learned about this while I was making this talk. I just moved to Massachusetts, so this is newer for me. But this website right here, But if you just type in resilient MA, you'll get all this data. So they'll do climate projections. They have tons of really, really interesting things like flood maps where climate change is projected to flood the coastal cities and towns of Massachusetts. Lots of really interesting information on that website. So not just projections, but also what's happening right now. So good data if you're looking for climate data. And then in addition to this website, which is good for Massachusetts, these are great websites. And if you're on Twitter, this is a great Twitter handle to get climate data. So Climate Central made a lot of those plots that I showed. I mean, climate.gov and NCEI have just tons of data that's free for everyone to look at. So those are the best sites, in my opinion. And the last thing I want to show is a hurricane forecast for 2019. You can judge for yourselves whether these forecasts are any good. So this is 2019 here. There's projected to be 5 hurricanes. So that's slightly below normal because we will have a weak El Nino, which means because there's an El Nino, we'll have above average wind shear. So that's primarily how they determine whether or not there'll be an active or inactive season. There are slightly above, there's always slightly above average temperatures at this point. So these are predictions from the past. This comes out of a group from Colorado State. And the black holes, the black dots are how many we actually got. So some years they're great, some years they're not. So this is primarily an exercise just to get people aware that the hurricane season is coming, in my opinion. These results are not very good. But that is the forecast of 5 per year. So, and that's all I have. So I'll take any questions if you have any. Yeah.
Well, with increasing moisture in the atmosphere, how do you explain, the likelihood of more droughts? That's going to happen.
Yeah, so it's the same mechanism actually. So you can hold more water in the atmosphere, so it takes longer for that water. So you can hold more. It's like having a bucket. You can put more water in it before it tips, but it takes longer for it to reach that point where it's actually saturated. And then when it does rain, it's heavier. But in between heavy events, it's actually a longer period of time where you're waiting. So you can have the two at the same time. Yeah. Yeah.
The question that you asked, was this specific hurricane caused by human activity? That's a question a lot of people are working on.
Oh yeah, definitely.
So my question is, why is that an important question to answer?
That's a good question. One is that if we can determine that human activities are not responsible, then it's just natural variability, and we don't necessarily have to plan for more of that event in the future. So
it seems to me that the probability is a much more ominous prediction than the specific hurricane question. That is, if we're only looking at one hurricane at a time, we can sort them into bins, then we kind of forget the ones that are not caused by human activity. Whereas if you say that the probability is that we're going to have X% more extreme weather events, that's a much more problematic statement.
I think the probabilistic way of framing it is better, because it's not an easy yes or no in general.
So I think people in general would like to have the specific, maybe the evening news would like to be able to say, this hurricane was caused by humans.
Right.
Or this one wasn't.
Right.
But what they ought to be saying is that this hurricane is X% more likely caused by humans than not.
Yeah. So they don't want to say that because it's not an attractive thing to say to get into probabilities. But that is exactly what it is. And when I showed this one, I put them here as strong evidence or no evidence. These were also always expressed in terms of probabilities as well, and that is the way that these all happen. So X event was 10% more likely or 10% less likely or not. Yeah, that's the way that we should frame this. The other reason why you might care about that, and this gets into a gray area, is litigation, suing somebody. So there's currently 8 climate-based lawsuits in the U.S. right now. So California, so San Francisco and I think Oakland tried to sue Exxon and Chevron for climate damages that I believe that case was thrown out. But
For one particular event?
I don't know if it was for a particular event, but it was for the damages caused by climate change, which are primarily from these individual events. So,
There was
yeah.
a thing on 60 Minutes where there's children have formed a lawsuit against the United States for not protecting them.
Yeah, exactly.
From life, liberty, or whatever. And
Right.
It's actually, I guess, gone through a couple of
Yeah, that's still potentially going to be, yeah.
courts.
Yeah, so that is one reason to do it as well. If you can attribute events to CO2 and you know that these are the emitters of CO2, then there's some potential lawsuit there. Yeah.
I was speaking to a geologist about this warming, and what he said to me was that the earth warms and the earth cools. And his opinion was this is a warming phase, and it can't be stopped. What is your opinion about this trend?
Whether it's natural or not, it's absolutely not natural.
It's not.
No. The Earth does warm and cool. I don't think I have a plot. Actually, maybe I do in my extra slides. Okay, so this is a plot of temperature going back 10,000 years. I didn't show this in the beginning. These obviously come from, a bunch of different, they're called paleoclimate proxies. So a classic one would be like a tree ring. These tree rings don't go back this far, but that's an example of one from over here. This is average temperature, I think in the whole northern hemisphere globe. I'm not entirely sure which, going back that long. So certainly we have been warmer than we are today. That's happened in the past. But look at this rate of change right here, right? This is because of human emissions. And we were in a cooling phase, certainly with the last ice age, and then we were much warmer at this period. This is largely because of orbital changes in the Earth's orbit in relation to the sun, and then we've been slowly cooling. And then there are, this is the little ice age potentially here, late 1600s, 1700s. But yeah, this is human caused. So that argument is true. The Earth is warming and cooling, but that's generally just, that doesn't explain what's going on right here at all.